Hi everyone, I'm Arshdeep. Today I will be talking about our work, structure-aware prediction with jointly optimized neural dependency graph. We understand the world as entities and the relationships. For example, if you're asked to find a path between your bedroom and the kitchen, you're likely to picture the entire floor plan, understand the network between the different rooms, and then determine the optimal path from the room to the kitchen. From a machine learning perspective, relationships are essential to make predictions. For example, if in this toy dataset, we are asked to separate the orange and the blue points, we need to take into account the interaction between x1 and x2. In most graph structured data around us, like chemical molecules or social networks, the graph is known beforehand. However, in some cases, the relationships may be unknown. To better understand a method, let's consider an example. So we are given data from different plays of a basketball game. Each play is a sample T. The different players, denoted by X, interact with each other to try and score a basket. The question we try to answer is which players coordinate or interact with each other and influence the play outcome. Our proposed method, dependency graph aware prediction or DGAP, extracts macro knowledge in the form of neural dependency graph and then uses the learned relationships to make predictions at the same time. DGAP is composed of two modules, a structure learner and a task learner. In the structure learner, we represent each edge between two variables, xi and xj, as a binary variable zij. Zij follows a Bernoulli distribution parameterized by gamma. Given a candidate dependency graph Z, to evaluate Z, we reconstruct X using Z. So we reconstruct each node Xi from its neighbor or parent nodes determined by the dependency graph. To see how well Z fits the data, we use the reconstruction loss. Our goal is to use the dependency structure for the target task as well as use the target task to learn a good dependency structure. For this purpose, we use a graph attention network as an interface that jointly represents the dependency graph as well as the input features. Using a graph attention network, we obtain node embeddings for each node in the graph. We're interested in a graph level representation, so we use a CLS node that is connected to all the other nodes in the graph. And we use this representation to make a prediction. We train DGAP using the sum of the prediction loss, the structure loss, as well as a sparsity regularization on the graph parameter gamma. We evaluate DGAP on multiple datasets like simulation datasets from Gaussian distributions, as well as real-world datasets that are tabular DNA sequences or text datasets. On simulation dataset, we note that DGAP discovers the correct graphs while being comparable in its classification performance. Further, the graph parameter gamma converges to the ground truth over the course of training. On the real-world data, DGAP is interpretable in the sense that it discovers semantically meaningful interactions while having competitive performance to its baselines. For example, on the transcription factor binding dataset, DGAP discovers a cluster of densely connected nodes that actually corresponds to a known motif for MYC binding. On text dataset, we observe a general relationship that local neighbors depend on each other. On the dataset about housing price prediction, DGAP discovers a relationship between latitude and longitude, which is relevant for house value prediction. Similarly, on heart disease prediction dataset, we observe a stronger link between the maximum heart rate and age in healthy class, while a weaker link for the same case in heart disease patients. In conclusion, DGAP is a modular interpretable framework that is an end-to-end framework that identifies dependency edges and uses these relationships to make predictions. Thank you for listening and feel free to ask us any questions.